Today's session, we will be looking at graph machine learning. An introduction with live demo is what the focus. It is going to be a pretty short discussion. We're going to have 1.5 hours of session today to introduce you to the graph machine learning as a field of study and the advancement that is currently happening in this field. Agenda for today's session is to introduce you on what is graph and what are all the different frameworks and the graph storage options which are available in the industry, and introduce you one of the prominent graph framework called tiger graph, and we will see a demo on that, and introduce something called graph neural network and how the graph neural network as such works, and followed by introduction of a deep graph library and the demo of that deep graph library and their architecture. So this is what the goal of today's agenda.
Prasanna, if you
So
don't mind, can you mute others, please? If you don't, yeah, I could hear a noise. Thanks, thanks.
sure. uh, Great. um, so we all are very familiar with a graph based representation, and whatever that we are currently interacting with, pretty much everywhere we see a graph based representation. It could be a chemical formula of a particular drug. You could represent and understand the details as a graph. And similarly, this is London's actual structure of how their subway system is structured. You can actually represent them very well on a graph based representation. Similarly, if you look at this is the first diagram is specific to Facebook's friend request details, how far it is going across the world, and that is being represented visually. This can very well be represented in a graph. And similarly, you take a human brain, and the human brain can be very well structured and represented on a graph based representation. I'm sure most of us would have got a very high level familiarity on what is a graph at a very high level structure. Let us go quickly have an introduction of what we talk about a graph and the representation of the graph, and how the graph basically help us in the whole process as such. Uh, if you look at this is an example of a Twitter tweet. How is it being represented? When you look at a simple tweet, there are various different details are being incorporated. It could have users who could be posting that particular tweet. That particular tweet might be mentioning a specific user, and it could have some hashtags as part of it, and the same tweet could be retweeted, and that tweet could got some replies, and the tweet can contain a link and so on and so forth. So much of information on a single tweet could represent a large amount of knowledge in that. A representation of this knowledge can be very well addressed using a graph based representation rather a typical tabular or other form of representation. We all are familiar with our tabular representation, and majority of our machine learning models that we are looking at predominantly utilizes the tabular representation of the data for processing. But what is a disadvantage on that tabular representation is some of the important things or important relationships that are represented in the graph are missed out in the tabular representation. To give you an example, this tweet could be an example that you can think, where how the tweet is interacted with multiple user. If you want to understand who are all the users who have used. You wanted to classify, you wanted to understand more about this particular tweet. It could be a very difficult process when you represent them in tabular format, and also utilizing the machine learning for understanding the details could also be a very tedious process. And typically your graph consists of the majority two different items. One is nodes and another one is edges. The nodes are nothing but the items that you are currently seeing in the screen, where represented by this tweet is a node, and the user is a node, and hashtag is a node. And these nodes are connected with something called edges. These are connected with edges. These node could have just a single feature, or it could have multiple feature as part of that particular node. For example, user as a single node, it could have multiple details as part of a feature specific to the user. It could have a username, it could have the whether he is male or female. It could have what date he registered with Twitter, and what date he is posting, what date he last posted, and so many details are being represented. These details represents a feature specific to that particular node. It is the features are not only for the nodes but also for the edges as well. The edges can also have a special set of features. And the post could be containing multiple different details, features in terms of what language that post was done, what date that post was done, and from whom the post was actually created, and so on and so forth. These are some of the examples. So if you look at the evolution of the database, as we know, I'm sure all of us might have a very clear understanding on our, good old relational databases. We used to work on our SQLs, MySQL, SQL servers, and so on and so forth. Some of the problems on the relational databases, if you look at, the schema is rigid. The schema is nothing but, you can imagine that you could have created a table to represent your data. If you talk about the tweet could be a table that you can represent them in the relational database. Some of the problems that we came across in the tables, once you have the table created, once you have created large complex relationship with the table, using foreign keys and so on and so forth, it would be very difficult for you to basically modify the schema structure. That is a basic problem. And but they were very well for high performance, for transaction based processing. Your atomic capabilities are well managed in a typical relational database. But you want to do some deep analysis, and you wanted to apply some analytics on that particular relational database. It had a lot of limitation in terms of how much of an analytics can be applied on them. Then we have come to the world of key value based or document based databases, like you could MongoDBs, and there are so many varieties of databases that came out. And these databases had a beautiful feature of fluid schema structure, and they provide high performance, but they lack the perspective of utilizing them for a deep analytics as such. So that's where the graph based representation came, where the graph based representation enables you to build things in a very flexible schema. You can do some complex transactions on them, and it also supports deep analytics and so on and so forth. Okay, so this is how databases have evolved, and how we have moved from a relational database to a graph based database. Now let's understand some of the basic premises in the case of a graph based representation. As we said, uh, some places you could represent this particular entity as a vertex or a node. Some companies represent them as vertex, some companies represent them as a node. And when you have two nodes, the connection between the nodes are represented by edges, and these vertex can have multiple properties or features. So does the edge. Edge can also have multiple properties or the features. This is an example of a user as a vertex, occupation as a vertex, and the user's occupation as a edge connecting with the particular user to a specific occupation. So this is a typical representation of any graph-based item. So now here is an example of how your actual vertex and the edges can have multiple features as part of them. For example, here the tweet has got two different features: the tweet date and time. And similarly, this particular node, this is an edge, this particular node has got two different features, and there is no limit on the number of features that you can actually add as part of the node or as part of the edge. So this represents a complete representation of a graph, or the proper these are called properties or features. It's all used one way or other uh, as you use them. Okay. Yes. Processing, there is a command from Mali. Processing graph might be difficult in a relational or no non-relational database. That we will see them. So I agree and also disagree on that. uh, Tip how we are used to work with various frameworks, like various tools and technology like SQL Server, MySQL, and your MongoDB, and so on and so forth. There are tools and technology which are available specifically to enable you to work with graph-based structure, graph-based data, and so on and so forth. Even if you look at a graph-based structure, when you look at a schema, let's say you take a tweet as a schema, the tweet is going to have comment and favorite count. These two could be a specific column. You could imagine from a relational database perspective, this tweets could be considered as an individual table. Along with that, you have multiple different columns on the table with different values. All these columns are connected in a very different way, and it is not just connected, this connections also going to have list of different features. You can consider the connections are also going to be acting as kind of a different tables, and these tables that you will have different features or the properties that you will connect with the corresponding representation. You can imagine that from a relational database world as such. Okay, that is from a graph database introduction. So if you look at in the industry, from a graph perspective, just to answer your question, you are familiar with, I'm sure, on various different frameworks in terms of relational or document-based database. And now this is specific to graph databases. So your graph database management system, these are different graph database management systems that are available in the industry right now. And to give you some perspective, so Amazon Neptune is a recently the launched service from AWS, which allows you to work on graph-based data items as such. Neo4j he, were available from for the last more than 10 years, more than a decade, for graph-based representation of your data. And the beauty of it is Neo4j is basically a open source solution, and the other solution is basically a tiger graph, uh, which is a proprietary solution from a company called the tiger graph, and they provide an option of creating and managing the graph database management and systems and so on and so forth. So these are various different other providers who are providing their, and Neo4j is open source one, and AWS Neptune and Tiger Graph are predominantly popular in the area. There are various different other frameworks were also available that I'm not covering here. On today's session, we will look at the Tiger Graph, and specific to machine learning perspective, we will look at something called a deep graph library as such. Even Tiger Graph provides a detailed set of 50 plus algorithms in terms of supporting your machine learning specific operations, but they have some restrictions in terms of accessing those platform for free, because they have a restricted access. You need to register and they need to provide the details and so on and so forth. Rather, we can utilize some open source library for the demonstration as such. Conceptually, pretty much everyone performs a similar kind of an operation as such. Okay, so that is in terms of graph database and database management systems which are currently available in the market. So from the actual among the top providers, if you look at the Tiger Graph is predominantly doing well on leading in terms of providing an innovative solutions. Let's look at the Tiger Graph perspective. What are all the different features that they are providing? So there are four different, main focus or the features of a Tiger Graph. One is to represent your data. They provide something called a Tiger Graph database, which you can imagine from a relational world, similar to that of your Microsoft SQL Server or a MySQL database. But the data will be represented and stored in a graph structure, and they provide a lot of different feature. Massive parallel processing is one of the important features that they provide, meaning one of the biggest hurdle in terms of representing and storing the graph database is in terms of how good of a processing power you should have to store and manipulate the graph data. So they provide a parallel processing for your graph. That meaning in the back end, they provide a parallel systems for representing and storing your graph so that the performance of your graph execution goes manifold. In terms of comparison, there are studies available in the market. If you want to do some two depth analysis, like I will two hop analysis that you wanted to do on your graph, then Tiger Graph performs outperforms pretty much any graph platforms available in the market as such. So that is only from a graph database perspective. The next important thing is you have the graph database. How do you query or retrieve the data? So we typically utilize SQL as our mode of interacting with our typical MySQL or SQL Server relational database. Similarly, Tiger Graph has something called GSQL. GSQL represents GraphSQL, which is somewhat similar to what you will do in a typical SQL server. All your typical where classes and all were available, where you will be able to specifically filter and provide the details and get the corresponding response from them. And these two are specific to the database. And the next is in terms of graph data science library, which is interestingly a open source library, meaning all this library are available as a Python library. You can directly download and utilize and modify as you wish. They have 55 plus graph and unsupervised graph machine learning algorithms available for you to directly utilize as a open source one. Right. And the next is this is a recent launch of Tiger Graph, which is called ML Workbench. This ML Workbench allows you to actually utilize your IPython like environment or your Google Colab kind of an environment. They provide customized version to enable you to utilize Tiger Graph for developing your machine learning workflows and pipeline. They have a very good connectivity in terms of connecting with any of the platform. For example, if you are working with AWS SageMaker for your pipeline, your machine learning pipeline, And as part of your AWS SageMaker pipeline, you want to utilize a Tiger graph based data. You can very well utilize the ML workbench to connect as part of the existing pipeline that you have, and utilize that graph database as part of your delivery as well. Similarly, they have one for Azure machine learning as well, so on and so forth. So these are four important features, or four important items of Tiger Graph as such. So now, as I said, which is a distributed parallel computing platform, and which can actually help you do a real-time analytics on the data that you have. As I mentioned, massive parallel processing is allowed, and support multi-hop query. What is meant by multi-hop query is assuming you have a graph and it has, let's say, multiple children nodes, and assuming that you are here in this particular node, you wanted to uh, search for some item available here, and for that you may have to hop 1 2 3. So this is 3 hop that you may have to do, and this multi-hop operations are possible in the case of Tiger Graph database query as such, using your JSQL. It also provides everything as a cloud-based access, so you do not need to install or configure anything. They also have a version for you to utilize as part of your local deployment in your enterprise environment as such. So that is at a very high level introduction. Let's look at the architecture, how what are all the different bits and pieces of the Tiger Graph as such. The left side part talks about different data sources that can be integrated with the Tiger Graph, and the right side talks about your enterprise infrastructure. You have some data that is coming from either your social media feed. You can get the data from an external RDBMS or Hadoop, Spark, log file. All this information you can load into your Tiger Graph using an ETL loader, and the Tiger Graph provides a storage engine and a processing engine. This is the base and core of it, and you have all the three options. You have an on-prem deployment, or a cloud deployment, or a hybrid deployment option. So on top of this, your graph storage engine, you have user-defined functions, a standard user-defined functions which are available for you to utilize, or you can create custom user-defined function. And on top of it, you have graph query language. This is the GSQL that I was talking about, and graph visualization. And we will see this too as part of our query. You can expose this as a REST API or Java C++ libraries to external world. This can be consumed by your enterprise business intelligence application analytics platform, or you want to have your dashboards, reports, your data warehouse, wherever that you want. You can actually take this data and process it. And this is somewhat latest update from their architecture as such. They have expanded the kind of data, like you can have the master data or your operational data information, and you could use anything like Spark, streams, files, anything can be directly integrated as part of your graph storage engine and graph processing engine. On top of it, you have a Graph Studio server to interact with the actual graph database. We will see that in a demo very shortly. And you can write the GSQL for interacting with them. And effectively, you can input the data, you can expose this as a RESTful service, and visualize the details into UI, and provide queries and execute the queries directly on the platform as such. And once you get the output, you can take that output to whatever that you want as part of your enterprise as such. So that is a overall structure of Tiger Graph Studio, Tiger Graph architecture as such. Now, as we said, they provide an option of you to create your own graph databases. like your Visual Studio or your MySQL Workbench. uh, TigerGraph also provides something called TigerGraph Studio, which allows you to create your complete end-to-end graph-based data management solution. So this starts with designing your schema. The schema is nothing but you want to create your table before you insert your data, right? So that defining your table in terms of a relational database is defined here as a schema. So in as part of your schema, what you will do, you will mention all the different dots you want, all the different vertex you want, all the different edges that you want between these vertexes, and what are all the different features that you wanted to have for these nodes and the vertexes. That is what you will do in the defined schema. And the next step is you will map the data to graph. So mapping of the data could, as in the previous slide we looked at, it could be a streaming data. It could be a simple CSV or text file. It could be anything. That data can be configured that this is my source of data, utilize this particular schema. And in this schema, this data goes to this particular node, this data goes to this particular edge. You define these detail as part of your mapping. And the third step is once you map, you tell load this particular data. So there could be a real time processing where you can have the data being loaded on a very real time basis as well, or you could load the data at one time. So one time loading of data. Once you have all this, all the graphs and the details are structured, you can query the data using GSQL and visualize what is the outcome that you are getting as part of the tiger graph as such. So that gives a high level overview of our tiger graph. And what we will do is we will directly switch to our live demo of the tiger graph so that you will understand how the whole structure works. Now, tiger graph, as part of their solutions, they already built some of the use cases as a demo, as a test driven solution. You can utilize them to visualize the details there. And here I will be using their test driven item for basically to visualize the details. Now I'm switching to uh, exiting from my presentation. Okay, so I'm switching to my screen. Um, as I said, this is the link for your live Tiger Graph system with the Graph Studio UI is being provided. You can visualize and enjoy whatever solution that you want. I'm going to utilize this social graph for my demo purpose. So this social graph consists of a billions of record of social media information. So let's take, for example, as I said, these are different steps that you may have to do. The first step is in terms of design schema. Now, in the design schema, it will display a already predefined schema as part of this. Now, here, these are different nodes. And when you move over to the node, you can see the details in terms of different features or properties of the node. For example, the social media talks about a citizen. A citizen has this vertex has so many different features: his name, date of birth, email, gender, ethical group. And it has a bank account detail. For example, let's say this bank account, what is the bank account, whether he owns it or not, that information is stored in the edge. And if you go to the bank account has the account ID as one particular feature. And similarly, the flight event, if you look at the flight details, the event ID and the event date are mentioned. And similarly, you have flight ride details are maintained in the actual edge. Likewise, you can actually refer the multiple different features which are available as part of your edges, and also your actual nodes there. So now, if you look at, you have defined this schema, assuming that you are creating this particular graph, you define this schema. Effectively, this particular solution does not allow me to edit it, but you can still, once you get access, there is a free version, free tier is provided. You can get an access and you can play around with this particular solution. The next step is basically to map data to the graph. As I said, the data source can be from anything, and here in this case they have updated the data from different CSV files. So here, for example, this is the original graph schema that we defined, and there could be multiple different CSV files that you could have, and you can upload this CSV file. And within this CSV file, you might be having a specific set of information that you wanted to connect to this particular nodes and details. So these connections are basically being defined here. For example, this CSV file has got the name of the CSV file is as such hotel records. This CSV file has got these many rows or columns as part of it. And what you do is, you have to specify for the hotel room event, which is nothing but the node, and for that, what is the actual detail has to be connected. Similarly, for this is basically an edge, GSQL connect. So basically, this is okay. There is a custom GSQL connect. What it does is it computes a multiple input details and creates a custom output out of this GSQL connect. And using this output, it creates a column for this particular hotel details. Okay, this is from this particular connect. If you look at, there is also one more connection that is going on in terms of for the edge. If I select that, now you can see that the hotel stay is an edge. The edge is also represented with multiple different sources, and what multiple different features and what information has to be connected there, that is represented by this. You wanted to build a custom column live while the data is getting loaded. You can build the GSQL connect by which you can create multiple details, combine them together and build a custom column here, and that gets updated when the edges are being created. So this represents the graph is not just your node and your edges, but it represents a multi different features of individual node and also the edges. Once you complete mapping the data to the graph, the next step is loading of data. In this process, what happens is the actual data gets loaded. As this is a test bed, this data is already loaded. So effectively, the total vertex, the total number of vertex that you see as part of this is around a billion vertex, a billion in B. Okay, and the total edges is around 2 billion edges. That is the amount of data that you can handle with the graph data structures. So that's the beauty of utilizing the graph based representation with the massive parallel information for your processing. Now, once you have this data being loaded, the next step is you want to explore the data and the graph. You can do them by using this explore graph. And you want to have how many vertices that you wanted to pick, and you can represent them. And you wanted to double click a specific item, it will actually provide you the details of what vertices, and that vertices was connected to what you wanted to understand about it. You can understand in detail. This is actual data. Previously, what we looked at is the schema, and now it is a data loaded item. So in the data loaded, so effectively it gives the details specific to individual vertices and the details that are being displayed there. Okay, so I can come back and pick. These are This represents a beautiful representation of how the data is being provided there. For example, let me just click here, or I can click a specific one, and it will load the details specific to that particular bank account and the details and so on and so forth. You want to do a specific vertex ID based one, you can do that as well. For example, all these options are available. You can choose based on whatever the details, room event, bus transport event, you can choose, and based on which you can provide the details. And based on that, the search result will vary, and the search result will provide the details in the graphical format as such. It's a very beautiful way of exploring different relationships that you are that are there as part of your graph as such. Okay. So so this is how you actually visualize and explore the details there in the graph. So we talked about it is not just exploring. You can write custom queries, so that is also possible as part of uh, your your tiger graph. So that is where this write query part comes in play. Here is where you will write the GSQL queries. Now they have provided the GSQL query details. So this is one GSQL query that is there to filter the specific details there. When I run that particular query, it will ask what is the details that I want. So let's say I am putting 100 and 200. I'm not sure whether it is going to come. Let's see whether there is B or citizen. So you get the actual vertex number details. You can basically get the corresponding details there. So here I've given some random numbers, and based on that random number, there is still a specific vertex with that particular number is available. On that vertex number, you basically have the details. All the details are represented here, and you can explore that particular person, and you can explore all the details specific to that particular person, and so on and so forth. This is how you utilize the power of your query language to actually create and explore a graph based structure. So till now what we are looking at is how you can actually create a graph based database and insert some data, and you basically visualize the data and query the data there. But effectively our goal is, why don't can't we utilize some of the capabilities of the machine learning world? How can we actually utilize that and apply it part of the graph based solution so that we get a proper response as part of it? So that is our goal as such, right? So let me just switch to my presentation. So that is what we wanted to achieve. Let's before we look at the graph machine learning as such, so where and all the graph machine learning has already been implemented and already started creating a lot of values. So we all are aware, we all might have used one way or other your Google Maps. The Google Map has some interesting feature called uh, your um, your destination time prediction. For example, you choose your you want to go to your hometown or a town which is near to you, and you put your details like this is my source and this is my destination, and find out how long it is going to take for me to reach there. Pretty much in the recent past, if you would have experienced it, Google Map would have provided you with much more accuracy as part of your actual yeah, expected time of arrival prediction, because the behind the screen implementation was done purely from a Google that is using graph based solutions as such. One example is in terms of uh, this, and Google has collaborated with DeepMind, the DeepMind has created a specific algorithm using graph nets and super segments for building their Google's ETA prediction as such. Using that, they were able to increase the accuracy of prediction by over 50% in, say, in China, and almost 40 plus percent accuracy was increased in Sydney, Australia. So this is how much of an increase in the actual prediction accuracy they could actually bring in. In the recent past, if you would have noticed, predominantly their ETA time were very accurate with plus or minus 5% of mistake. So that is achieved by using the graph neural network and graph machine learning as backend as such. Okay, so the other use cases that we can utilize as part of graph is, for example, a fraud detection. This is a very famous scenario in terms of banks and the credit card providers. Assuming that a particular customer utilizes a specific set of cards using specific set of devices at specific set of location. So that is what the information the graph already has, and you have the location information, your devices, and it's different set of cards that you have used. Assuming this customer is using this, the historic information is used, suddenly a new location has popped up which is completely not related to the customer, or a new device pops up, or new card pops up from the customer. So these are some of the events that can actually help you identify fraudulent transactions in the case of credit card or debit card usage. So the other use case is in the case of recommendation engine. I'm sure we are all used to watching Netflix and Prime videos and so on and so forth. And how does Netflix or the Prime identifies what to recommend? So here in this case, let's say there are Chinu as a sample person, and should we recommend this particular movie? If we recommend this particular movie, what could be the rating that Chinu will provide? This is a problem statement, because the main goal of the providers like Netflix or Amazon Prime could be that you want to recommend a movie which you will like a lot so that you will rate more. So how can they identify the details? This can be very easily identified by using graph based representation. In terms, if Chinu has actually done uh, rated multiple other movies, understand the genre of that particular movie, and where she has connected with how other people have actually rated similar to Chinu, who have rated this particular movie, and based on which you can actually identify, okay, if this person similar to Chinu and this person is also similar to Chinu already rated this particular movie, and if they have rated this particular movie high, I am sure that Chinu also will rate this particular movie high, so we can recommend this particular movie to them. So it's a recommendation engine. So this is how currently your Netflixes and your Prime all recommendations are work. I am sure that this is going to get expanded across all the thing that you are doing. It could be you go to a grocery shop, it will recommend you what are all the things that you want. It's all happening already as well on many cases. So the next is a drug discovery perspective. So here in this case, you have a combination of multiple chemical structure. With this combination, what kind of a new drug that I can discover specific to pharmaceutical institution? This is it's a no brainer, it's a fantastic option of providing the details there. So how does this happen? Basically, you have the graph based information available there, and you have a pure machine learning which can actually predict and classify the detail. A combination of your machine learning and your graph data structure to build something called graph convolutional neural network. We will see a graph GCN as a demo as part of today's session. you will basically combine the features of your graph and also with the neural network to build this graph based machine learning solutions. Okay, that is how you do that. So we will see how to do that. So you are saying that you will do this, how to do that. We will see that shortly. But before that, we talked about Tiger Graph. These are some of the group of algorithms that they provide as part of graph-based data science library, which is an open source library. One is in terms of shortest path identification. This you could use from Google Maps. You use a source and destination. You wanted to identify what is the shortest path to reach there. This algorithm can actually provide multiple options. You can identify which is the shortest path. Centrality affects within the particular graph what is the importance of a specific vertex that can be provided using centrality. Effectively, all the search engine utilizes the centrality feature for your best search algorithms, and so on and so forth. The next is community deduction. You see a specific set of graph subgraphs or acting similarly. You identify a specific community, and the community deduction can be done by using the set of algorithms. I'm talking about only the high level items where each and every item consists of multiple set of algorithms. And similarity, for example, I have some items I wanted to see a similarity of as the same way. Like just now we looked at an example of uh, Chinnu wanted to actually see that particular movie. We are looking at a similarity of who are all the people who have rated similar to Chinnu, and if we can identify that, we can use them for recommendation engines as such. And the classification, it's a no-brainer from a machine learning world. A similar classification that you are doing in the machine learning world, you can utilize as part of the graph-based solution. So topological link prediction, it's basically to predict the existence of link between two entities as such. And graph embedding, we will see an example of how the graph embedding is going to work. And this basically helps you. So your one of our friend asked the question. So your representation and the manipulation of the data in the tabular structure is very easy. That is why majority of your machine learning algorithms were focused on your tabular structure. So now, how do I apply an algorithm that was created for a tabular structure to a graph based structure? One option is you can create something called a graph embedding to convert your graph structure to a tabular structure internally, so that you can apply the typical machine learning algorithms as part of them. That is part of graph embedding. The next is frequent patents mining. So you see frequent patents avail which is getting recorded. It could be it could be used in terms of your ticketing system, in terms of your support system, a specific set of queries and specific set of problems that is getting occurring or at a specific set of time frame. You wanted to understand what is going on. Once you have frequent pattern mining algorithms in place, the log files can be mined to understand such patterns so that you can do a predictive analytics on them. So these are some of the set of libraries which are available as part of Tiger Graph. Now, let me just introduce you how the graph neural network as such works. So we talked about in the previous slide something called graph embedding. Okay, so effectively, how does this graph embedding as well work? So this is from the original network, that is your graph network. You create something called an embedding space, which is a lower dimension embedding space where you represent these individual vertex available there and also the relationship details as an encoded details in the embedding space. It may sound very complex, but it's very simple. You think of this, each and every vertex that you are having and your edges that you are having, imagine them as a matrix or a vector. Rather a matrix, you consider them as a vector. So you represent these vectors at a lower dimensions of a lower dimension. That is what is going to be an embedding space. So it is not just this embedding, which is the initial step. What are all the different manipulations that we can do so that we can build a effective neural network or effective graph neural network as part of it. So this slide just to give you how the actual graphs are represented as an encoded nodes at an embedding space. The encoded node, what it does is this particular node details are encoded as a simple vector represented there in the embedding space as such. So, so how does this graph neural network works? So, effectively, assuming you have a graph like this, and in this graph you wanted to do the graph neural network operation as such. Okay, so the actual neural network operation is nothing but it learns the node edge and the graph embedding. Okay, so what it means, like, let me start with this particular node. So I'm here in this particular node. So this particular node can be represented with a graph embedding. You can imagine that as a vector, as a simple matrix. Now, if this particular node is connected immediately with this green color nodes, so now what, how the neural network, graph neural network works is in terms of on the first run, it will first learn the details about this particular nodes, these particular nodes, and based on the details from this particular node it will update the embedding vector or the matrix of this particular node. Is it clear? So embedding of this particular node utilize this particular node that is connected to this the center node and update the vector of the central node. That is on the first round. In the second round, what it does is it goes to the next level. So these nodes are getting updated from the, for example, if you take in the second pass, you take individual nodes like this, and these nodes are connected to multiple other nodes, related nodes. Now this particular node will get updated with their related values, and once this is updated, again this information will get updated to this particular node. So this will get updated to this, and this will get updated to this. So now if you look at, it's a two hop effectively from this node. Because this embeddings data is updated, it now learns about what is there connected to it, and also what is there it has connected to the next level of details. So that is the amount of information that it is actually learning from it. So you represent them using an individual set of network. So this hop you can define as part of your graph neural networks. You know how many hops that you want to go to learn and update these details. The more that you put, the more complex the network is going to be, the learning is going to be as such, from the graph neural network perspective. So that is what represented here in this video. So assuming in the node that is represented by a vector, and you have a projection for the nearby nodes, they all have a vector, and all of them are going to update this particular central node. Okay, and in the next step what happens, it is going to take the data from all the nodes which are connected to this that particular second node, and they will update and update the details back to your original node. So that is in the input layer. The first is input layer, and the GNN layer 1, this is graph neural network layer 1. Again, this is graph neural network 2. So that is what is represented in this particular diagram as such. Okay, so so what would be the outcome of such operation, assuming that you have an input, and the actual graph learns about it and provides an output, and what would be the outcome of it. So now there could be three possible outcomes you can utilize as part of it. One is node classification and graph classification and the link classification. What is this node, graph, and link classification? We saw an example before. Here, in the first one, we talked about a customer, which is nothing but a node or an vertex, and now effectively predicting whether this particular node or vertex is having a fraudulent data or not. So that is what our requirement there. So this can be classified as a node classification. Now, in the second example that we looked at, whether Chinu can we recommend this particular movie? Here, what we are looking at is whether Chinu will rate it or not. So, which is an edge classification. We also looked at something called your whole drug prediction. So your drug prediction requires not just your single node or edge, but you require a complete structure, complete graph. So that is a graph level prediction, graph level classification as such. So this is what these are the different type of things that could be an outcome of your graph neural network as such. You could be focusing on a from a graph neural network, you could be focusing on a node level prediction or an edge level prediction, or your graph a complete graph level prediction as such. But in the case of a typical machine learning, the thing would be completely different. It could be like you could be using that for your classification activity, or you could be using it for your regression or specific activities as such in a typical machine learning one as such. So this is a basic difference that you can see. Okay, there are now you understood how a typical encoding matrix is created, encoding vector is created, how the graphs are being manipulated, and so on and so forth. There are two other variances. There are many other variances are there. I have taken only two. One is called message passing neural network in the graph, and the next one is called graph sage. So in the case of message passing neural network, how it works, I will quickly walk you through on how this is going to work so that you will understand. So assuming that you have a graph like this, and this graph, let's take only two of the node. So from this two of the node, we will build a message using a specific function, because in the typical graph neural network that we saw, it talks only about the node that you have taken, but it does not bother about the actual edge, and also there could be various other features of it. So you will provide different weightage for the different features, and you will create something called a message, and this message will get created, and this message will get updated to that particular edge, and in turn it will get updated to the final node. You will get message for this particular node, this particular node, this particular node, and all this will get updated back to that particular node that you are working on. And with that update you will get a new value for the specific node, and that new value that you have created, you will update it back to the actual node itself. So you started with a specific value h4, and you wanted to create a message and build the message for all the nodes which are connected to it, and update that particular value back to that. You call it as h4 plus 1. So this updated value, you will you will repeat this process for all the nodes that are connected. So when you complete this message passing, all the nodes will have an updated information with the message. The message consists of not just the node specific information, its edges, and also a weightage to the kind of information that is being exchanged between them. That is called message passing graph neural network. So the next variance is when the size of the graph goes very large. We have today looked at a bill social graph in the tiger graph, where you had over a billion nodes. When you have such a large node, it would be very difficult for you to actually process the node and the data details. So that's where a new variety of graph algorithm came called graph sage. So here, instead of taking the complete graph, it takes a sample neighborhood of the graph. From the billions of nodes that you got, you take probably a million node, and you create the aggregate feature information and using the neighbor information, that everything, and you build and predict a graph's context using the data that you have taken for your prediction as such. Okay, so this is basically a subgraph that you will use for your actual processing. Instead of processing the whole graph, you define that you wanted to take only a million node for your processing. You start from one random node and identify all the million nodes which are connected and process it accordingly. So this graph sage was taken by Pinterest. I'm sure most of you might have heard about a company called Pinterest, and this Pinterest already utilizes the same algorithm. They call it as Pin Sage, and this Pin Sage basically been implemented for a 3 billion nodes. Imagine the kind of nodes that you're talking about, 3 billion nodes, to actually classify and provide better images for you. If you are sitting there in India, if you utilize Pinterest, the kind of image that you are going to get would be completely different from somebody who is sitting in US or UK, who will be looking at these images as such. So the next so now we looked at the graph neural network and introduction of it, and how the neural networks actually learn. We also looked at graph convolutional network and so on and so forth. Now we'll see how do we actually implement that in the program as such. We have a library called Deep Graph Library, which is promoted by AWS, which is a complete Python based open source library available for you to work on a deep graph based operations as such. This is the architecture of uh, the, the actual DGL, where the beauty of the DGL is it can work with both PyTorch, TensorFlow, and also MXNet for your actual operation. And the DGL provides your DGL runtime and graph handling, and your neural network modules are available. And there are specific graph algorithms are provided as part of it. You can utilize it for your processing. On top of this, they have two specific library. One is called DGL Life Science, another one is DGL Knowledge Graph. These are specific domain focused solutions on them. Yes, Mali.
Prasanna, before going here, only the question is
Yeah,
earlier, anytime if you send a message, the
yeah,
graph is completely getting updated. Somehow you said like they are doing new techniques to make at least in neighborhoods only.
correct,
But the end, anytime, see, a lot of messages might be updating every time for the data.
correct, correct,
So the map is almost, it is like it's live. Every time it is getting updated and sending messages. Meanwhile, maybe another message getting updated like this. It
correct,
will be very
correct,
often.
correct.
So in that case, maybe
Yeah,
do you think like it takes a lot of processing time, or maybe it takes some time more than what a traditional
yes,
data stores?
yes. So effectively, what how it is being handled is based on subgraphs. So it is not in the, for example, if you take in the Google Maps, and Google Maps backend is predominantly maintained by graph. The whole
Mhm.
structure is maintained in graph. Now you are in a street, and in that particular street there is suddenly something happens. There is some thousand people have started walking in the street. Now, because they are walking in the street, there is a huge traffic flow. Now, on a every minute basis, this traffic information gets transferred to the actual graph, and this graph gets updated that this particular route is blocked. So when somebody searches for going through that particular route, what happens is this information is lively processed and the graphs are updated already that this route is blocked for some reason and you have a blockage in this particular route and better utilize a different route, or it will tell you have a delay on the ETA preparation as such. So all these are live, all these requires huge amount of processing, and predominantly how they will do is they will do a subgraph based update. To give you an example, assuming that you are say in New Delhi, so they could take New Delhi as a separate graph and they'll be updating New Delhi as a separate graph, and parallelly they could be taking Bombay as a separate graph and updating. So these two does not require to be updated on the same machines. It's a distributed learning is possible now. So your Bombay could be managed in a different server but in the same graph, and your Delhi could be managed in a different server but in the same graph. Hope it makes sense. Hope you've been able to
Yeah,
understand what I'm saying.
I
Yeah,
understand.
so
The
that
point is definitely did more than what a relational or a table data is processing. Graph
yes.
data processing might took more efforts or more processing, I would say. Is it right?
Uh, not necessary in the sense you're talking about uh, for querying the details and extracting the details.
Yes.
It is at par and even above par details. The reason being, when you wanted to query a specific relationship,
Mm-hmm.
because these relationships are already defined in the graph, you already have these relationships are much better understood in the graph. The graphs are much better in a position to actually provide the response. uh, so to query a billion social details,
Mm-hmm.
the tiger graph takes to query and extract a subgraph details from the billion nodes. Tiger graphs takes around 2 to 3 seconds, and
Mm-hmm.
in relational database, it is literally not possible to put that billion data. And even comparatively they have done, and they have done an analysis with open source library without parallel processing. If you do
Mm-hmm.
that without parallel processing, that query actually fails in say neo 4j and all. So this was done by some third parties and provided that details. So 2 to 3 minutes what you can do, you cannot even manage the data in the relational database, and in
Correct.
other libraries you actually fail that particular one. So yeah.
Understand. Data storing, yes, we can understand. This is more complex, which is might not be possible to store in a relational data with very good manner.
Yes.
That clear.
So the updations that I'm talking about is, yeah, the updation that I'm talking about is only for your machine learning operations. Okay. So when it is come to a typical database as such, it is going to be a plain database. The queries could be a plain queries. When you want to do some intelligence on the data that you have received, that's where this updation, the details that we are talking about will happen there. When you
Understand.
want to,
Clear.
yeah, when you want to use a graph neural network, that's where this updation and all happens there. Okay, until then it's a plain database, that's it.
Okay. Adding to this,
Okay.
just I got some other clue there. Let's suppose how we are storing the data or messaging other nodes is almost like a blockchain, I would say. Is there any, yeah, am I right in thinking that
The blockchain is basically um, a single
the case
structure
is
in the
like,
sense
yeah,
there
it
is
is a
no.
single structure. All other
Yes.
nodes must be
you
updated
can
before they
you
get
can
updated.
represent, yes, you can represent, but the difference is once blockchains are created, you won't have any update on them. It's once it is created, that's a beauty of it. You will not be able to go back and update the details in the blockchain
Hmm.
as such,
Hmm.
right? That's the difference here. Yes, you can represent the blockchains as a graph. That's a beautiful way of representing that.
Yeah,
Yes.
fantastic. Thank you.
Thanks. So yes, DGL is another library similar to TigerGraph, right? Yes, or else it's a subset of, no, it is a separate library. TigerGraph is a separate framework, and DGL is a separate framework, money. So it's a completely new library which is promoted by Amazon, AWS, DGL as such. But TigerGraph is a separate company altogether. They promote their own set of libraries and frameworks and so on and so forth separately. Hope it clarifies. Right. So, so next is let's do a live demo. So for this live demo, what I've taken is in terms of there is a Quora data set which is already defined and uh, processed as a graph-based data set, and this Quora data set consists of research papers that are published, which are available in the industry. These research papers are considered as nodes, and the edges are represented as citations. The citations are nothing but the details. The research papers could be used by somebody else. So these people who are using this research paper will reference this particular research paper. That is called citation. So that is what we're going to do in today's session. And the source code for this is already uploaded in the GitHub. You can enjoy, and this code is basically not mine, effectively provided by DGL, and you can enjoy. There are various different algorithms they have provided, and that same details I have taken, and I have used Google Colab for the representation here. Now let me just quickly go to the source code and provide do the processing. So reconnect. Let me just okay. So I'm using Google Colab for the actual execution. So as part of the Google Colab, first thing is I need to make sure that my Colab is connected properly. Yes, my Colab is connected. Now let me just try. I need to install DGL. This is a command to install the DGL in this one, and let me just try importing this. If it is imported, then that means, yeah, so I've already installed it. I don't need to install it again. So I have imported DGL, and I'm going to use PyTorch for your demo. And the PyTorch has NN for your neural network and functional for your different functions in terms of your activation functions and various other functions that you are using, that we will be using F. Okay. Now, the first thing is the dgl.data. I'm importing the data from something called Quora graph dataset. Let me execute it. When I execute it, it will actually load the dataset. The number of nodes are 2000 nodes. Number of edges are around 10,000 edges. Features, number of features are 1,433 features. Number of classes are 7 different classes. So it already has a training, validation, and test samples, and the details are available here. So there are 7 different category of data which is available here. Now what we are going to do is do a node classification using graph neural network. Okay. So node classification is nothing but in the whole we just looked at, there are 3 different outcomes that we can do from a graph neural network. One is you can do a node classification or edge classification or your whole graph classification from the graph neural network. In this example, we'll be doing a node classification as such. So node classification, using this, there are number of classes, 7 classes are available, uh, and that is what we will do. So now assuming that I will take this data set and move it to a variable called G, and it will have these details: training mask, validation mask, test mask, nothing but a tensor representation of the data, which is nothing but a test training set, validation set, test set, and the labels and features are represented here. and the end data is nothing but your node data, and e data is edge data. So if I just execute it, the node data and edge data are displayed here as tensors. Now we will define the graph convolutional network, GCN. So now for defining the graph convolutional network, DGL has, as part of their neural network library, I am importing this graph convolutional network. I am defining this graph convolution network. I will create two different layers. There is one convolution, convolution 2. In the first convolution, the input features are taken, and that will spit out the intermediate features, and these intermediate features are taken as the second convolution. And in the second convolution, input is the intermediate feature, and the output will be number of classes. So it is basically a classification problem. Identifying node classification problem is what we are planning to do. In the feed forward, we will be using ReLU as our activation function. And first we will do convolution 1, and in the ReLU we will apply, and then we will do convolution 2 and return the corresponding outcome there. And using this, you build the model, and we call it as this particular model GCN with the data, node level data details that you are sending, and number of classes information that you are sending with the dimension details. Now this is for defining the model, creating the model, and for training you need to define how you are going to train. So as part of the training, you've defined basic details. What is optimizer, Adam optimizer you will use for your algorithm. There are different features that you will have from the different variables that you have: node data, node label, and training mask, and your validation and test mask. You basically move the details to your variable, and we're going to do 100 epoch. And in this 100 epoch, you call the model with the actual details. And once that details one forward is complete, you do argmax of 1, and you do the prediction, and apply a cross entropy for losses. And once you get complete that, you do compute the training accuracy, validation accuracy, and test accuracy. You, for each and every epoch, you take the best accuracy value, and if that best accuracy value is less than the current validation accuracy, update that particular value. And you basically repeat this, and I'm going to print this only at the time of every 5 epoch. And I call this model GCN and repeat this whole process. Let me just execute it. Oops, okay. So I need to execute this. I forgot to execute it. Let me just execute this. Let me execute this. Now it is working. So now if we look at 95 epoch, because that is how we have taken. Here in this case, we have a classification task with a loss of zero point 0.1. It's only 10% loss, with the validation accuracy of 77% and test accuracy of 76%. 76%. So that is how it's as simple as you building a typical machine learning library. You basically created a graph based, utilized a graph based algorithm, and built your graph neural network for your processing as such. So this code is available already as part of your GitHub library. You can utilize it. So that brings to the end of graph neural network introduction as such. So I'm happy to answer any questions the team has. I hope it is clear.
Yes, Prasanna.
Wonderful. Yeah.
Yes, Prasanna.
If uh, if there is no question, so I'm happy that I will share the recording of this session to all of you guys. And thank you very much for on Saturday putting your time and effort and attending the session. Okay, thank you very
Thanks,
much.
Prasanna.
Yes.
Thanks very
Thanks.
much from our side, Prasanna, which needs to be conducted on Saturday so that we can attend without any fail.